Hello students, so continuing our lectures on mathematical physics, we will start with matrices. Uh, Basically, we will discuss about the types and the definitions of different types of matrices. Focus on the types and definitions. So first we will start with the matrix which is called an identity matrix. So this is given by, say, matrix I2 is equal to 1 0 0 1. The reason it has been named I2 because it's a second order matrix, 2 cross 2 matrix. Similarly, you can have a 3 cross 3 matrix as well, is given as I3. It is 1 0 0 0 1 0 0 0 1. These are the identity matrix. Next, we can think of a matrix called a scalar matrix. Scalar matrix is when you multiply an identity matrix with a scalar. That means it is given as, say, A11 0 0 A22. That means it is only having scalar values as its diagonal elements. It could have been A11 as well, or rather A. So this would have nothing but A into I2. Similar to that, we can have a 3 by 3 matrix as well. So it's A11 0 0 0 A22 0 0 0 A33. This is what an identity matrix is. The next is the scalar matrix. Sorry, asymmetric matrix. So symmetric matrix is that matrix where uh, the elements, that means a ji is equal to aij. That means this, for example, is a symmetric matrix. So all the, say, you have a11 here, a22 here, and a33 here. Apart from that, all the other matrices which have different I and G values, like we have A12 here, so it should be equal to A21. So instead of writing A21 here, we also write A12. Like if we have A13 here, this would have been normally A31. So instead of that, we are writing A13. Similarly, these two will be equal. It's A23. This would have been A32, but we are still writing A23. So this matrix, these two are equal. This one and this one are equal. All the non-diagonal matrices, all the non-diagonal elements are equal with respect to interchange of the indices. This is a symmetric matrix. However, if the case is opposite, that means they are equal but there is a slight change in sign. That means the case is such that this is AGI is equal to minus AIJ. That means all the matrices are equal. That means let's write the diagonal elements first. A11, A22 and A33. To non-diagonal elements, this is A12, but the place where there should be A21, it is minus A12. Similarly, if this is A13, this is also A13, but it is minus A13. This is A23, this is also A23, but it is minus A23. So interchange of indices keeps the value same but only changes the sign. So then that matrix is called a skew symmetric matrix. So the next type of matrix that we will discuss, discuss something called inverse of a matrix. Means if you have a matrix B, which is actually inverse of a matrix A. So if that is the case, then AB should be equal to I and Untitled matrix. And another widget is that AB inverse should be equal to B inverse into A inverse. The order changes. This is inverse of a matrix. Then we can have something called a commutation value. That means if A commutes with B, then it implies that AB is equal to BA. And if it anti-commutes, then AB is equal to minus of BA. This is commutation property. And then we another type of property is the transpose of a matrix. A transpose is when you interchange the rows and the columns. That means if your matrix, say 1, 2, 3, 4, this is say A. So the A transpose will be simply, if you interchange this and this position, that would be 1, 3, 2 and 4. This is the transpose. And there are some properties related to the transpose matrix. They are A plus B transpose is equal to A transpose plus B transpose, and A double transpose, if you do it, then you get back the same matrix, and factor multiplied to a matrix, and then if you transpose it, it's factor, there is no change in the factor multiplication, it's k into A transpose, because it is being multiplied by all the elements of the matrix. So this is what about transpose. Next property is called the conjugator matrix. So So if the elements of a matrix are complex numbers, and if we replace each number, each element is replaced by its conjugate. So it's actually each element replaced by its conjugate, then we see that the matrix is a conjugate matrix. Suppose you have an element where it's given as 1 plus 2i, then 2, say 3i, 1, 2i, 1 minus 3i, 2i, 1. If this is the case, let's call this one as matrix A. So if this is the matrix, its conjugate, which is represented by, either you can call it as A bar or A star, is when we will replace each and every element by its conjugate. So those numbers which are not complex numbers, they will remain the same. The only difference will happen to those which are complex numbers. So 1 plus 2i, its conjugate will be 1 minus 2i. This will be, there won't be any change in 2 because it's not a complex number. 3i will be replaced by minus 3i. I will be replaced by minus I. 1 plus 3i will be 1 minus 3 will be 1 plus 3i. 2i will be minus 2i. So all the elements. So if we do these operations, then we get the conjugate of the matrix. The next property is called trace of the matrix. Trace. Trace is nothing but addition of all the diagonal elements of a matrix. So it's represented as TR is equal to summation of AII. It is a matrix say 1, 2, 3, 0, 5, 4, 6, 2, and 8. Then the diagonal elements are 1, 5, and 8. So just you need to add it. 6 plus 8. So the trace is 6 plus 8 is equal to 14. This is a trace. Great. So the next is your the next type of matrix is called Hermitian matrix. Hermitian matrix. So if transpose conjugate of a matrix gives you back the same matrix, then you call it as a Hermitian matrix. It is also sometimes represented as a dagger. A dagger means you transpose it and then you conjugate it, then it's a Hermitian matrix. Or in terms of elements, if Aij is equal to Aji, so by converting Ij to Ji, you are transposing it, and then you are converting Aij to A bar Ij, that means you are conjugating it. So another property of an Hermitian matrix is the diagonal elements are real numbers. So diagonal elements are real numbers. That means they are not complex numbers. So this is an important property of a Hermitian matrix. So the next type of matrix is called an orthogonal matrix. So it has to be a square matrix first of all. If the square matrix is said to be an orthogonal, if A, suppose is the square matrix into which conjugate gives you an identity, is identity matrix and is also equal to A conjugate into A. Or in other words, we can say that if the transpose of the matrix is equal to the inverse of the matrix, then we say that the matrix is an orthogonal matrix. So another property associated with an orthogonal matrix is the column vectors or the row vectors are of an orthogonal matrix are mutually orthogonal unit vectors. Say that the column or the row vectors of an orthogonal matrix are mutually orthogonal unit vectors. This is the first point of an orthogonal matrix. The second point is that the inverse and the transpose of an orthogonal matrix are orthogonal. So number 2 is it is called as number 1. Number 2 is the inverse and the transpose of the orthogonal matrix are orthogonal. This we have already seen here. That means if A inverse into is also an orthogonal matrix and A transpose is also A transpose is also an orthogonal matrix. And the third point associated with an orthogonal matrix is number 3. The third point of an orthogonal matrix is the product of any two or more orthogonal matrices is orthogonal. The product of any two or more orthogonal matrix is orthogonal. And the last point is the determinant of an orthogonal matrix is plus minus 1. Determinant, that means A is an orthogonal matrix, the determinant will be equal to plus minus 1. So these are some of the properties associated with an orthogonal matrix. The next type of matrix is called a unitary matrix. Okay, now a linear transformation, for example, if you have a y is equal to a into x, where a is a unitary and x is a vector, it is called unitary transformation. So this happens to be a unitary transformation, and where x is actually a vector. By vector we means that it is either a row matrix, a column matrix, or a row matrix. So if if the matrix is unitary, then another property is that the linear transformation preserves length. Next is called the rank of the matrix. Now, if determinant of the matrix is not equal to 0, it is called a non-singular matrix, and if it is equal to 0, it is called a singular matrix. Now, a non-singular matrix is supposed to have a rank R if one of its R square minors is non-zero. If one of its R square minors is not equal to 0, while if every R plus 1 minor exists and if every R plus 1 minor exists and it is 0. So by minor, what do we mean by a minor? Suppose we have a matrix given as A11, A12, A13, A21, A22, A23, A31, A32, and A33. So minor, this is a 3 cross 3 matrix. So its minor will be any 2 cross 2. Any 2 cross 2 matrix will be its minor. So we can take up either this one as its minor. We can take up this one as its minor. Or we can also take up this one as its minor, or this one as its minor, or any combination. So what it says that if its rank will be equal to 0, suppose the rank of this matrix is 2. So it means that every 2 cross 2 matrix will be non-zero and every 3 cross 3 matrix will be equal to 0. Had it been a 4 cross 4 matrix, let's say take a larger example. Say a matrix A11, A12, A13, A14, A21, A22, A23, A24, A31, A32, A33, A34, A41, A42, A43, and A44. So this is a 4 cross 4 matrix. So here, if we say that the rank of the matrix is 2, here we are saying that the rank is equal to 2. In every 2 cross 2 matrix, the determinant is non-zero. So if at least one of its, not all, every one of its R square matrix, any one, is a non-zero. However, every 3 cross 3 matrix, that means we say R plus 1 matrix, this is equal to 0. So if you take a 3 cross 3 matrix, this is a 3 cross 3 matrix, can have a lot of combinations of 3 cross 3 matrix. So every 3 cross 3 matrix it exists and it is equal to 0. By minor, we also mean that it's the determinant 1, 2, 3, 4. And the minor, if it is being multiplied by, say, if Aij has got a minor and it is being multiplied by a factor -1 I plus j into the minor, then it's called the cofactor of the element Aij, and it is used in the inverse calculations, and you get the adjoint. That means if we have a matrix A, then A inverse is actually the adjoint of A divided by determinant of A, and adjoint of A will be actually equal to all the cofactors of all the elements of A. That means cofactor A11 if it is a 3 cross 3 matrix, cofactor of A12 and so on and so forth. And by cofactor we mean that had it been the matrix A11, A12, A13, so cofactor of this A13 will be determinant, this corresponding diagonal determinant. This will be its minor multiplied by I plus j, I minus 1 to the power 3 plus 1. That's how it will be. So if we divide this one by the inverse of the determinant, we get the inverse of the matrix. Then we have some elementary transformations associated with the matrix. And the first elementary transformation is the interchange of ith row and jth column. Interchange of the ith rows and jth rows, or interchange of ith column versus jth column. That means if a matrix say 1, 2, 3, 4, 5, 6, 7, 8, 9. If I either interchange these two columns, that means it can be now 4, 5, 6, 1, 2, 3, or 7, 8, 9, or it can be interchange between these two and these two. Then it's called the interchange. Or what we can do, we can interchange between these two. So now if you interchange between the first row and the second row, then the matrix will now become 2, 5, 8, 2 5s, 8, right? 1, 1, 4, 7, and 3, 6, 9. So these two are examples of interchange. Okay. Now the second type of elementary transformation is multiplication of every element of the by a scalar. The second one is multiplication by a scalar. The matrix say 2, 3, 4, 1, 2, 3, 1, 2, 1. And if you're multiplying with the scalar k, say k is equal to 2, so every element will be get multiplied by 2. So it will be 4, 6, 8, 2, 4, 6, 2, 4, 2. This is called scalar multiplications. And the last type of matrix or elementary transformation is when say an ith row, so third type of transformation, when the ith row element is added with the scalar multiplication into the jth row, then this is called the row elementary or row transformation. So if we have a matrix, say 1, 2, 3, 4, 5, 6, 7, 8, 9, then you are say multiplying the first row or the first column. So let's take the first row. Row 1 is being replaced by row 1 plus 2 into row 2. So we multiply each and every element of this row 2 by scalar 2. So it will be, so instead of 2, 5, 8, now it will be 4, 5, 4, 10 and 16. So the first element will be of the first row will now be replaced by 1 plus 2 into 4, 2 into 2, that is 1 plus 4. This will be 4 plus 2 into 5, that is 4 plus 10. And the last one will be 7 plus 2 into 8, that is 7 plus 16. And the rest will be same, 4, 5, 8, 3, 6, 9. So this is called the row elementary or row transformations. Or it can be in the column as well, or it be in the different case. So 2 multiplied by all the elements of the second column plus addition to the first column. Okay, so the next topic is when we say that the two matrices are equivalent. When do we say that the matrix A is equivalent to matrix B? So if A is obtained, or say if A is obtained by some elementary transformations on B, or vice versa, or B is obtained by some elementary transformation of A, then we call that A is equivalent to A. And the last topic that we will discuss is called the characteristic equation. Let us consider there is an element ax, that equation is equal to lambda x. So A is a matrix, say n by n matrix. This is a column vector or a row vector. So if we do this multiplication, we get back the x, and with the value lambda, this is called the eigenvalue. So we get the characteristic equation if we multiply, if we transform the Lipid transformation of this equation, and we write it in this fashion: a minus lambda I into x is equal to 0. And for this equation to get satisfied, the determinant of this part should be equal to 0. So by this we means that every diagonal element will be now replaced by minus lambda I. So it will look something like this. It will be now a11 minus lambda, a12, a13, a21, a22 minus lambda, a23, a31, a32, and a33 minus lambda. So all the diagonal elements are now have changed. This and determinant, we take determinant of this, we get an expression from where we actually find the value of lambda, the eigen values. And there are the characteristic roots. And lambda and this x is called the eigenvector of the equation. One more topic is left, that is called diagonalization of a matrix. How do we diagonalize a matrix? That means we make all the non-diagonal elements as equal to 0. How do we do it? So we can do it by say we have a matrix A and we need to diagonalize it. So we find a matrix C such that a diagonal matrix S is equal to C inverse AC. So this is, then if this is the case, then we say that this is the diagonalized form of A, and S will have the characteristic roots as the diagonal elements. So it also says that S will have the characteristic roots, that means the lambda values or the eigenvalues as the diagonal elements. So it will be now say the lambda 1 0 or any element, lambda 2, lambda 3. Then we say that we have diagonalized the matrix.